Alright, so here we are with Unit 8, Lesson 4, and this is where we're going to begin to look up or look into what we call potential energy diagrams. So potential energy diagrams, as you can see here, is something that you need to memorize, potential energy diagrams. You remember back when we did heating and cooling curves and you had to memorize both of them? It's the same thing here with potential energy diagrams because there are both exo and endothermic potential energy diagrams. And a potential energy diagram basically keeps track of the potential energy content of the substances in a chemical reaction as they go from reactants to products, and then it's graphed. Now you're not going to be asked to graph. You're going to be asked to identify the different parts of a potential energy diagram, be able to identify it as being either exo or endothermic, and a couple other things as you'll see as we go along here. So a couple of things you can look at here. We talked about the heat of reaction. The heat of reaction, which is abbreviated delta H. Remember the delta, the triangle means change in heat. All chemical reactions involve the loss or gain of energy. This energy is heat energy, potential energy. So when you hear heat of reaction or delta H, they're asking about how much heat was either given off or absorbed during a chemical reaction. And if you look down here, it's giving you the two different kinds, exo and endothermic. And if you look, actually, if you have reference table I, and we've talked about reference table I before, so I'm not even really going to go through this, but you do need to fill this out. I will check that when I go over your notes. At the bottom of table I, it gives you a hint. It says at the bottom of table I something to the effect that negative delta H values indicate an exothermic reaction. So any reaction that's on table I that has a negative delta H value is going to be an exothermic reaction. Any reaction that has a positive delta H is going to be endothermic, and that pretty much is what is talked about right here. So I'm not going to go through all of this stuff here. I'm not going to go through this at the bottom either, but you do need to fill that out because I will be checking that. Next thing is that these potential energy diagrams can be read in two directions because we have what are called reversible reactions. Not all reactions, but some reactions can go in two directions. One's called the Fode reaction, and this is the reaction that you normally see. You know, A reacts with B, and it produces C and D. Until now, we've said, well, that's pretty much it. Well, we've kind of not told you the entire truth. Because there are reactions, not all reactions, but there are some reactions that once this initial reaction occurs, the Fode reaction, then C and D can then react and reproduce or reform the original reactant. So you can sometimes have two things occurring at the same time. The Fode reaction is A reacts with B and it produces C and D, but at the same time you can also have C and D reacting and reforming A and B. So you have two things going on. Fode reaction, which is read from the left to the right, and the reverse reaction, which is read from right to left. Now, instead of writing two different equations, what we would do is we would indicate it using an arrow that points in both directions, which you will see later on. Next is activation energy. This is an important definition. Activation energy is the amount of energy that's needed for a reaction to start. And some reactions require a lot of activation energy, some don't require much at all. But you can see, and you'll see this when we go through the potential energy diagrams, how this is involved with a catalyst. If you remember, we said that a catalyst is one way to speed up a reaction. A catalyst speeds up a reaction by reducing the amount of activation energy that's needed to start a reaction. There's also something that would slow down a reaction that would be the opposite of a catalyst. That would be an inhibitor. I have yet to see that term ever on the Regents exam, so I'm not going to really worry about that. So a catalyst speeds up a reaction by lowering the activation energy, and this is a typical potential energy diagram. This happens to be an exothermic one. How do I know that? Well, if you look at, and we pretty much ignore the x-axis in potential energy diagrams, and we look at the y-axis, this is potential energy. This measures, this is the amount, and this is a graph. There's no numbers on it, but this represents, this line right here would represent how much potential energy the reactants have. This is how much potential energy the products have. Notice how the products have much less potential energy than the reactants, which means it lost energy. That represents an exothermic reaction. So one of the ways to represent or to recognize an exothermic potential energy diagram is to compare the reactants and the product's energy. If this part is lower, that's an exothermic reaction. If this part was up here, that would represent an endothermic reaction. And you'll see that in a few minutes when we go over the diagram. So before we get into the diagrams, let's this is lesson 4.